Okay, so here are my random witterings to try and help with question 2 from the test part of the energy efficiency lesson. This question a bit clearer for people from last week. So we're going to draw an energy transfer diagram. It doesn't have to be a Sankey diagram, nothing to scale. It's literally just saving us right is transferred into a lot. So we can use an arrow for that instead. So for A, we've got an object hitting an obstacle. Okay, so I'm going to imagine a car, yeah right, don't be rude about my drawing, hitting a wall. Okay, so the car was obviously moving at the start. The starting energy in my diagram is going to be kinetic energy. That kinetic energy is going to be transferred into other forms of energy during this collision, this hitting the obstacle. The main thing that's going to happen is it's not going to move anymore, it's going to stop, because all of the kinetic energy is going to be transferred in other ways. The car will no doubt squash and bend. There will be some elastic potential energy. Sorry, you're watching me right now, which is quite slow, I know, and not particularly neat. Sorry for that. There is also going to be a transfer of kinetic energy into sound energy. We'll hear the crash. You'll also find that there is thermal energy, always thermal energy. In fact, as this car squashes and bends, there'll be even more thermal energy, because that's basically what all of the kinetic energy will end up as. It will end up as thermal energy in two places and sound energy, which will all be dissipated to the surroundings eventually. Okay, in B, we have got a roller coaster going uphill. Time for another amazing drawing. There you go. There's my roller coaster. And it's going to go up. So it's starting at the bottom and it's going to climb up to the top. So at the bottom, it's not moving, but it's going to have to move if it's going to go up. So the input energy, as it were, in this situation is kinetic energy again. And the roller coaster is going to go up the hill. So as it moves upwards, kinetic energy is being changed into gravitational potential energy, GPE. And along the way, there's going to be some friction, some air resistance. There's definitely going to be some thermal energy wasted. You're not going to get all of the kinetic energy, 100% all become gravitational potential energy. Some of the energy is going to be wasted. It's not 100% efficient. You'll probably find there's going to be a little bit of sound as well in that transfer. But at the top of the hill, at the top of the roller coaster, I apologise, the main store of energy will be gravitational potential energy. Some of the energy that would have been wasted and dissipated to the surroundings. Okay, in C, we've got a car coming to a stop. Oh goodness, that means I get to draw my amazing car picture again. There you go, it looks a bit like a boot, doesn't it? Here is my car, and it's going to come to a stop. So there's no crash now, but there's something happening inside this car. There are brakes. And brakes work by rubbing together. Okay, they transfer kinetic energy of a moving vehicle into lots and lots of thermal energy, heats up the brakes, and then that thermal energy is dissipated to the surroundings. So we've got a car that was moving, so we've got kinetic energy at the start, and then the car comes to a stop because, I'm assuming here, the brakes are safely applied. So there is loads of thermal energy. And that thermal energy will first be in the brakes, and then there'll be thermal energy in the surroundings. And of course, there'll be sound, which goes straight to being dissipated to the surroundings as well. I hope that was useful and helpful, and do feel free to join a Google Meet and ask questions like that. I really should check the mark scheme before I launch into an explanation, shouldn't I? I have just had a quick look, and I will add one thing that Mrs. Bill had thought deeper about than I had for the second example for B, the roller coaster. So the roller coaster does have to move to get up to the top of the roller coaster at the start here. However, Mrs. Beale has thought about the energy that's actually gone into making the car move. It is most likely to be electrical energy, because most roller coasters have an electrical motor that pulls them up at the start. In fact, you might sometimes hear clunk, clunk, clunk if you've been on a roller coaster, as that electrical motor is pulling up the car from the beginning. So let's add that bit in to make an even better answer. We've got electrical energy being transferred to pull the car and move it up the start of the roller coaster uphill. Once it's at the top, that kinetic energy has been transferred into gravitational potential energy, but it wasn't 100% efficient because there was thermal energy and sound that got dissipated to the surroundings. In a roller coaster, once it's got to the top of that first climb, there is no more electrical input at all. The rest of a roller coaster is purely a transfer of energy from that original gravitational potential energy. That is why you never get to go higher than you did on that first climb on any roller coaster. Everything else is involved in trying to be as efficient as possible and waste as little energy as possible, but everything else that happens on that roller coaster ride comes from that store of gravitational potential energy. I hope that little addition added on there has made that even clearer.